developed by Planck successfully explains the emission of radiation by heat in solids. So mystery number 1, black body problem, was solved by Planck in 1900. Earlier, classical physics assumed that atoms and molecules could emit or absorb any arbitrary amount of energy. Planck's quantum theory states that radiant energy is emitted by atoms and molecules in small discrete amounts, known as quanta, rather than over a continuous range. This behavior is governed by the relationship E equals h times nu, where E is the energy of the radiation, h is Planck's constant, 6.63 times 10 negative 34 joules second. Nu is the frequency of the radiation. This equation can be rearranged to E equals h times c divided by lambda, where c is the speed of light and lambda is the wavelength of the radiation. Because as we previously covered, c equals to nu times lambda. Practice problem: what is the frequency, in hertz, of light having a wavelength of 566 nanometers? Try working this problem. C equals to nu, frequency, times lambda, wavelength, therefore, nu equals c divided by lambda. The answer is D. Using quantum theory, Einstein solved another mystery of physics, the photoelectric effect. Photoelectric effect is a phenomenon in which electrons are ejected from the surface of metals exposed to light of at least a certain minimum of frequency. Einstein proposed that light can behave like a stream of particles known as photons. Light has dual properties, that of a wave and that of a particle. Photon is a particle of light. The photoelectric effect study gave rise to the equation h nu equals to Ke plus W, where Ke is the kinetic energy, W is the work function. A measure of how strongly the electrons are held in the metal. W is also known as binding energy. Practice problem: when copper is bombarded with high-energy electrons, X-rays are emitted. Calculate the energy in joules associated with the photons if the wavelength of the X-rays is 0.154 nanometers. The problem is solved as shown. Practice problem: a particular form of electromagnetic radiation has a frequency of 8.11 times 10 to 14 Hertz. What is the energy in joules of one quantum of this radiation? Try working this problem. Answer B. E equals to h times nu. Practice problem: the work function of potassium is given. What is the minimum frequency of light needed to eject electrons from the metal? The problem is solved as shown. The line spectrum of hydrogen, yet another mystery to 19th century physicists, was also solved by applying the quantum theory. Each element has a unique emission spectrum. It is like a fingerprint of an element. Here is the line emission spectrum of hydrogen. Here are the line emission spectra of other elements. Mystery number 3, the line spectrum of hydrogen, was in part solved by Bohr in 1913. Bohr developed a model of the hydrogen atom in which the energy of its single electron is quantized, limited to certain energy values determined by an integer. The principal quantum number, according to the Bohr model, 1. Electrons can only have specific, quantized energy values. 2. Light is emitted as an electron moves from one energy level to a lower energy level. This is given by the equation energy equals to negative RH times 1 over n squared, where n is the principal quantum number, equals 1, 2, 3, dot, and RH, Rydberg constant, equals to 2.18 times 10 raised to negative 18 joules. An electron in its most stable energy state is said to be in the ground state. Ground state or level, lowest energy state of a system, n equals 1. An electron at an energy level higher than its most stable state is said to be in an excited state. Excited state or level, higher in energy than the ground state, n equals 2, 3, 4. In the Bohr model, an electron emits a photon when it drops from a higher energy state to a lower energy state. The release of specific amounts of energy in the form of photons accounts for the lines in the hydrogen emission spectrum.
The amount of energy absorbed or emitted by a photon or an electron can be calculated using this equation. Delta E equals to h, which is Planck's constant, times nu, which is frequency, and the whole thing again equals to RH, which is Rydberg constant, times 1 over Ni squared. I stands for initial, minus 1 NF squared, F standing for initial, and are the principal quantum numbers. So the electron went from I to F. If Ni equals to 1 and F equals to 2, then what you would put in bracket would be 1 over 1 squared minus 1 over 2 squared. If Ni is smaller than NF, delta E is positive. That means the electron has absorbed some energy. If Ni is greater than NF, that means delta E is going to be negative. The electron has emitted, released some energy. Let's take a look at this problem.
Practice problem. Calculate the wavelength in nm of a photon emitted by a hydrogen atom when its electron drops from the n equals 5 state to the n equals 3 state. The problem is solved as shown. Practice problem. An electron in the hydrogen atom makes a transition from an energy state of principal quantum numbers b to the n equals 2 state. If the photon emitted has a wavelength of 434 nanometers, what is the value of Ni? Try working this problem. Answer, n equals 5. electron energy quantized? Why is the electron in the Bohr atom restricted to orbiting the nucleus at a certain fixed distances? De Broglie, 1924, reasoned that particles, such as electrons, have wave properties. He reasoned that an electron behaves like a standing wave in the atom. The length of the wave n times lambda equals the circumference of the orbit 2 pi r. De Broglie extended Einstein's wave-particle description of light to all matter in motion. This is demonstrated by the following equation of wavelength. The wavelength of a moving particle of mass m and velocity u is given by the de Broglie equation. Lambda equals to h divided by m times u. U is in meters per second and m is in kilograms. Practice problem. What is the de Broglie wavelength in nm associated with a 2.5 grams ping pong ball traveling at 15.6 meters per second? The problem is solved as shown. Practice problem. What is the de Broglie wavelength in centimeters of a 12.4 gram hummingbird flying at 1.20 times 10 raised to 2 miles per hour? 1 mile equals to 1.61 kilometers. Try working this problem. Answer C. Quantum mechanics. Schrodinger proposed an equation that described the motions and energies of submicroscopic particles. This equation launched quantum mechanics in a new era in physics. First, the Heisenberg uncertainty principle states that it is impossible to know simultaneously both the momentum p and the position x of a particle with certainty. Momentum is mass times velocity. Delta x times delta p is greater or equal to h over 4 pi. Delta x is uncertainty in the position and delta p is uncertainty in the momentum. In 1926, Schrodinger wrote an equation that described both the particle m and wave psi, nature of the electron. Wave function describes 1. Energy of electron with a given wave function psi. 2. Probability of finding an electron in a volume of space, psi squared. Schrodinger's equation can only be solved exactly for the hydrogen atom. It tells us the possible energy states of the electron in the hydrogen atom and the probability of its location in a particular region surrounding the nucleus. We must approximate its solution for multi-electron systems. An atomic orbital is a function, psi, that defines the distribution of electron density, psi squared, in space. Electron density gives the probability that an electron will be found in a particular region of an atom.
Quantum numbers. Quantum numbers are the address of an electron. So they describe the distribution of electrons in atoms. They are derived from the Schrodinger equation, and there are four of them. So psi, wave function, is a function of n, l, ml, and ms. What are they? N is principal quantum number, L is angular momentum quantum number, ml is magnetic quantum number, ms is electron spin quantum number. So these are the addresses. These are the addresses of an electron. So let's start with the principal quantum number n. So the value of n goes from 1 all the way to 7. So n can be 1, 2, 3, 4, etc. And what does it describe? It describes the main energy level, or shell, and it tells us how far away the electron is from the nucleus. So you may have an electron at n equals to 1, at n equals to 2, or n equals to 3. So the electron that is at n equals to 1 is closer to the nucleus than an electron that is at n equals to 3. So now let's take a look at L, angular momentum quantum number. So for a given value of n, L equals to 0, 1, 2, 3, all the way to n minus 1. So the value of L depends on the value of n. What does it describe? It tells us the shape of the volume of space that the electron occupies. So if n equals to 1, L equals to 0. If n equals to 2, L equals to 0 or 1. If n equals to 3, L equals to 0, 1, or 2. If n equals to 4, L equals to what? 0, 1, 2, or 3. L, when L equals to 0, the orbital is called S. When L equals to 1, the orbital is called P. When L equals to 2, the orbital is D. L equals to 3, the orbital is F. S stands for simple, P for, what is it? Principal, D, diffuse, F, fundamental. Now let's take a look at ML. ML is a magnetic quantum number, and for a given value of L, the value of ML can go from negative L all the way to plus L, including 0. What does it describe? It tells us the orientation of the orbital in space. So if L equals to 1, which means it's a p orbital, the value of ML can be negative 1, 0, or 1. If L equals to 2, which is a d orbital, the value of ML can be negative 2, negative 1, 0, 1, or 2. So again, ML, the value of ML, depends on the value of L. The last quantum number, and that is MS, spin quantum number. So there are only two values for MS, plus 1/2 or negative 1/2. And this describes, spin quantum number describes the direction of the electron's spin. So it is either clockwise or counterclockwise. Okay? So now let's talk about atomic orbitals. So this is a review of what we just said. If n equals to 1, L can only be 0. And the value of ML, which is dependent on the value of L, can only be 0. The total number of orbitals you have here is 1. So if you just count how many ML values you have, you will find out it's 1. Now if n equals to 2, the values of L can be either 0 or 1. Now the values of ML will depend on the value of L. So if L equals to 0, ML will equal to 0. If L equals to 1, the values of ML may be negative 1, 0, and 1. How many orbitals can you have when n equals to 2? A total of 4, 1 plus 3. And then we can look at also n equals to 3. When n equals to 3, L can be 0, 1, or 2. The value of ML depends on the value of L. If L equals to 0, ML will be equal to 0. If L equals to 1, the value of ML will be either negative 1, 0, or 1. If L equals to 2, the value of ML can be either negative 2, negative 1, 0, 1, or 2. Now, if you want to count how many orbitals you can have when you have three shells, you have to add all of them up. So it will be 4 plus 5 is 1 plus 3 plus 5 gives you what? 9. So an S subshell has only one orbital. A P subshell has 3 orbitals, and that you can count by if L equals to 1, that is a P subshell. So you have 1, 2, 3, so that gives you 3 orbitals. If you have a D subshell, that means L equals to 2, you may have 5 orbitals, so 1, 2, 3, 4, 5. Okay, and the total number of orbitals for a given value of n is n squared. So you can use that equation. So we said for when n equals to 3, the total was 9. So if you can just square the 3, we get the same answer. Now let's take a look at s orbitals. There is one s orbital, spherical in shape and centered on the nucleus. Its size increases as the principal quantum number increases. If L equals to 0, remember we call the orbital S. So we said as the principal quantum number increases, the size increases. So you have 1s, 2s, 3s, and the size is increasing. Remember what an orbital is. It tells us where you can find an electron 90% of the time. So it tells us the probability of finding an electron at 90% of the time. P orbitals, there are 3 of them. So there are 3 P orbitals. They are identical in size, shape, and energy. The difference is in how they are oriented in space. So here you have 2 px, so it's taking the x-axis. Here you have 2 py, and here you have 2 pz. And they are all of equal energy. They have the same size, same shape, but the orientation is different. And then there are 5 d orbitals. They are identical in energy, but they have complex shapes and orientation. And this is all of them that we just saw. So this problem is asking you to list the values of n, l, and ml for orbitals in the 4D subshell. So if you have 4D subshell, and here's a hint, this is something we mentioned earlier, L equals to 1. If L equals to 1, the orbital is called P. If L equals to 0, the orbital is S. If L equals to 2, the orbital is D. L equals to 3, F orbital. So now we have 4D subshell, meaning that N equals to 4. And what is the value of L? The value of L is 2, because we have a D orbital, right? So what are the values, what are the possible values of ML? So we can go from -2, -1, 0, +1, +2. So here's a problem for you. There's an electron in an atom, is in the n equals to 3 quantum level. List the possible values of L and L that it can have. Take a look at this and tell me the answer. So if n equals to 3, the possible values of L are what? 0, 1, and 2. And if L equals to 0, the value of ML will be 0. If L equals to 1, the value of ML will be what? -1, 0, and 1. If L equals to 2, the values of ML equals to -2, -1, 0, 1, and 2. So the answer is C. In a single electron atom, the energy of the electron is determined solely by its principal quantum number n. Whereas in many electron atoms, the energy of the electron is determined by its principal quantum number n and the angular momentum quantum number L. So let's take a look at this diagram. So this is for a single electron atom. So if you have an electron at 2s, or at 2p, the energy level is going to be the same. Look at the y-axis, right? It says energy. So the 2s and the 2p orbitals have the same energy level. So energy only depends on principal quantum number n for a single electron atom. For a multi-electron atom, the energy depends on n and l. Okay? So if you put an electron in 2s versus an electron in 2p, the electron that is at the 2p will have a higher energy level than an electron that is at 2s. 2p versus 2s. Right? Now if you put an electron at 2p, 2px, and another one at 2py, then the energy level of the electron will be the same. But because the value of n and l are the same. But if you change the value of n or the value of l, then the energy level will be different. Okay. So an electron that is at 2s, the value of n will be 2, the value of l will be 0. An electron that is at 2p, the value of n equals to 2, the value of l equals to 1. So if you want to describe the location of an electron, you need to give the values of n, l, nl, and ms. So that tells us where that electron is. Now if you have two electrons on the same shell, then that means they have the same value of n. If you have two electrons at the same subshell, that means they have the same values of n and l. If you have two electrons in the same orbital, that means they have the same values of n, l, and ml. Okay? How many electrons can an orbital hold? Well, if we said that two electrons may have the same values of n, l, and ml. That means the value of ms would have to be different. It can either be plus 1 over 2 or negative 1 over 2. Therefore, the maximum number of electrons that an orbital can hold is 2. How many 2p orbitals are there in an atom? Okay, 2p means that n equals to 2. P means that l equals to 1. If l equals to 1, the values of ml can be either negative 1, 0, or plus 1. That means there are 3 orbitals. How many electrons can be placed in the 3D subshell? 3D means what? N equals to 3. D means L equals to 2. If L equals to 2, the values of ML may be negative 2, negative 1, 0, plus 1, or plus 2. So how many orbitals do you have? 1, 2, 3, 4, 5. 5 orbitals. And we know that each orbital can hold a maximum of 2 electrons. Therefore, 2 times 5 gives us a maximum or total of 10 electrons. So now let's take a look at electron configuration. What is that? Well, electron configuration will tell us how the electrons of an atom are arranged in that atom. So existence and energy of an electron in an atom is described by its unique wave function psi. And psi is a function of n, l, nl, and ms. We already gave a name for this. N we said was a principal quantum number. L was angular momentum quantum number. And L is magnetic quantum number. And S is the electron spin quantum number. So here's a practice problem. Give the values of the quantum numbers associated with 2p subshell. So if you have a 2p subshell, n equals to 2, L equals to what? 1. That means the values of ML may be negative 1, 0, or 1. So the answer is D. So electron configuration, one more time, is how the electrons are distributed among the various atomic orbitals in an atom. So for hydrogen, the electron configuration is 1s1. So what does this tell us? It tells us that the electron of hydrogen is in the first shell. So because the principal quantum number n equals to 1, the angular momentum quantum number L equals to 0, and it only has one electron. The superscript here tells us how many electrons are in that orbital. Okay, so orbital diagram, we can put it this way. We can draw it that way. The next thing we want to do is mention Pauli exclusion principle. Okay, Pauli exclusion principle states that no two electrons in an atom can have the same 4 quantum numbers. So you cannot have two different electrons with the same N, L, ML, and MS values. MS has to be different. At least MS has to be different. Okay, so this is an analogy. If you are in a casino and you are sitting, so you have a seat that is uniquely identified. So each seat can hold only one individual at a given time. Same thing if you are flying. If you buy a ticket, your seat is uniquely identified. Now let's take a look at the difference between paramagnetic atoms and diamagnetic atoms. Paramagnetic atoms are atoms with one or more unpaired electron spins. So they have at least one unpaired electron, and they are attracted by a magnet. Diamagnetic atoms are atoms in which all electrons are paired. They are slightly repelled by a magnet. So here's an example of a paramagnetic atom's unpaired electrons. And then here's another one for a diamagnetic atom. All the electrons are paired. For electrons of the same principal quantum number, that means the value of n is the same, their penetrating power or proximity to the nucleus decreases in this order: S, and then P, then D, then F. So what does this mean? If you have two electrons, one is in 2s, and the other is in 2p, the electron that is in 2s is going to be closer to the nucleus. Therefore, it will require more energy to remove it, because it will be attracted more by the nucleus, because it's closer to it. So more energy is required to remove an s electron than a p electron. Now let's state Hund's rule. This is another rule you have to know. What does it state? The most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. So, let's say you have carbon. Carbon has 6 electrons, and you are trying to figure out its electron configuration. So the first two electrons are going to be in the 1s orbital. The other two will go on 2s orbital. And the other two are going in 2p orbital. Remember, we have three 2p orbitals, 1, 2, 3. They are all of equal energy. They have the same shape, same size. The only difference between them is the orientation in space. So how do you put the other two electrons of carbon? According to Hund's rule, before you start pairing them up, each 2p orbital has to have one electron. And they are parallel to each other. So this is parallel spin. And so if you want to write the electron configuration, you would write 1s2, because it's filled, 2s2, and then 2p2. Now, if you have nitrogen, which has 7 electrons, so it has one extra electron than carbon, the 7th electron is going to the empty 2p orbital, which is of the same energy level as this other 2p orbital. So that's where it goes. And then the electron configuration would be 1s2, 2s2, 2p3. Now, if you have oxygen, which has 8 electrons, that means it has one extra electron than nitrogen, its 8th electron is going to be going here. It's going to be paired up, because we maximum number of electrons that all these 2p orbitals can accommodate is 6 total. Okay, so the 8th electron is going to go on the 2px orbital. It will spin in opposite direction, right? And the electron configuration of oxygen will be 1s2, 2s2, 2p4. Fluorine has 9 electrons, so one extra electron than oxygen. So the 9th electron is going to be paired up with this electron, with the opposite spin, of course. So the electron configuration would be 1s2, 2s2, 2p5. Neon has 10 electrons. Neon is a noble gas. So its last electron, the 10th electron, is going to be paired up. So neon has all of its electrons paired up. So its electron configuration is 1s2, 2s2, 2p6. So there is an order of orbitals, how you would fill the orbitals in a multi-electron atom. So first you fill out 1s, then you go to 2s, then to 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and so on. Okay? So here, let's do some examples. What is the electron configuration of magnesium? So what you do is you look up the periodic table and you find out that magnesium has 12 electrons. So that means you have to distribute all these electrons, these 12 electrons, according to the rule. You would have to fill up 1s before you fill up 2s, and then you fill up 2p until you run out of electrons. Okay? So you find out that you would put 2 in the 1s, another 2 in 2s, 6 in 2p, and then 2 in 3s. So the electron configuration of magnesium will end up being 1s2, 2s2, 2p6, 3s2. So that gives us 12 electrons. There is an abbreviated or noble gas notation where instead of writing the whole thing, you just write in bracket a noble gas that precedes magnesium, and then 3s2. 3s2 is the outermost electrons. The 3s2 means you have 2 electrons in 3s shell or subshell. So neon has this electron configuration 1s2, 2s2, 2p6. So instead of writing 1s2, 2s2, 2p6, 3s2 for magnesium, this is an abbreviation. All of this can be replaced by bracket neon. and then 3s2 is are the 2 electrons that are present in magnesium, so you put that. So what are the possible quantum numbers for the last or outermost electron in chlorine? So you do the same thing. You look up the periodic table, you find out that there are 17 electrons. So you follow the rule, you fill 1s before you fill 2s, then 2p, and then you go all the way to 3p, so 1s2, 2s2, 2p, 6, 3s2, 3p5 is the electron configuration of chlorine. That gives us 17 electrons. The last electron added to 3p is the outermost electron, right? So the answer will be, what are the possible, to the question, what are the possible quantum numbers for the last electron in chlorine? Well, n equals to 3, L equals to what? 1, because it's in p orbital, and you have 5 of them, and these 5 electrons are in what, and then what other values could they have? -1, 0, or +1. And their spin maybe 1/2 or -1/2. Okay, so this will be the answer to this question. N equals to 3, L equals to 1. The values of ML may be -1, 0, or +1, and the values of MS may be either 1/2 or -1/2. So let's take a look at some general rules of assigning electrons to atomic orbitals. Rule number 1, each shell or principal level of quantum number n contains n subshells. So if n equals to 2, there are 2 subshells, 2 values of L, right? 0 or 1. Rule number 2, each subshell of quantum number L has 2L plus 1 orbitals. So if L equals to 1, there are 3p orbitals. Rule number 3, no more than 2 electrons can be placed in each orbital. Rule number 4, the maximum number of electrons that an atom can have in a principal level n is 2n squared. So here's a practice problem. Calculate the total number of electrons that can occupy A 1s orbital, B 3p orbitals, C 5d orbitals, and D 7f orbitals. So each orbital takes 2 electrons. So if you have 1s orbital, that's 2. If you have 3p orbitals, that gives you 6. So 1 for A, for B it's 6. For C, we have 5d orbitals, so that means 10. D, if you have 7f orbitals, that's 14. So the answer is what? Yeah, let's see. So 2, 6, 10, 14. C is the answer. Indicate which of the following sets of quantum numbers in an atom are unacceptable. A has 1, 0, 1/2, 1/2. So the value of n equals to 1, the value of L is 0, and then the value of ML is 1/2. We have never seen a value of ML being equal to 1/2, so there is a problem with A. Now let's take a look at B. B has n equal to 3, L equals to 0, ML equals to 0, and MS equals to plus 1/2. Is B okay? B is okay. Let's take a look at C. n equals to 2, and then we have L that is equal to 2. So there is a problem right there. So C is not acceptable. Let's take a look at D. N equals to 4, L equals to 3, ML equals to negative 2, and MS equals to plus 1/2. D is acceptable. Let's take a look at E. N equals to 3, L equals to 2, and then L equals to 2, ML equals to 1, and then ML equals to 1. We have never seen an MS equal to 1. So E is unacceptable. Therefore, the answer to this question is D, A, C, and E are unacceptable. So let's take a look at the building up principle, or the Aufbau principle. What does it state? It states that when you are filling up electrons, you need to fill up electrons in the lowest energy orbitals first. In other words, you don't fill up 2p before you fill up 1s and 2s. Okay? And then there is something you need to take note of. Once you fill up 1s, you fill up 2s, and then 2p, 3s, 3p, then it's 4s before you fill up 3d. Then once you fill up 3d, you go to 4p. Once you fill up 4p, you go to 5s. After 5s, it's 4d. Then it's 5p, and so on. So filling up electrons in lowest energy orbitals is what the Aufbau principle is. So hydrogen, it has only one electron, so the electron goes in the 1s orbital. And this is the ground state, meaning the state at which the electron is most stable. If you have helium, which has 2 electrons, then you need to pair the first electron that you put in 1s. So the electron configuration of helium will be 1s2. If you have lithium, which has 3 electrons, then you have to put the third electron in 2s. So the electron configuration of lithium will be 1s2, 2s1. If you have beryllium, which has 4 electrons, you need to pair the electron that is in 2s before you put an electron in 2p, right? So the electron configuration of beryllium is 1s2, 2s2. Boron has 5 electrons. So the fifth electron goes in 2p. So electron configuration of boron will be 1s2, 2s2, 2p1. Carbon has 6 electrons. We have seen this before. We said we do not pair them up. That's Hund's rule, right? You need to first put one electron in 2px and another one in 2py and then 2pz before you start pairing these up, right? So this has the periodic table with the orbitals where the outermost electrons are going to be filled. Okay, so let's take an example here. Let's say you have lithium. Lithium is on the second period, right? So it's on the second period. So when you fill up the electrons, the last electron goes in 2s, and because lithium is right here. Now sodium is in group 1 and it's on the third period, right? So its outermost electron goes in 3s. Now let's take a look at fluorine. Fluorine is on the it's a halogen, so group 7, and it's on the second period. And its outermost electron goes on 2p. So this is telling you that it is 2p. Now let's take a look at titanium. Titanium is a transition metal. It's a transition metal it's on the fourth period. But when you put the electron, we put, if you remember, we said we need to fill out. Let's go back to what we said. Yeah, here, with the Aufbau principle. We said we need to fill up the 4s, and then it's 3d, right? So titanium's outermost electron goes in 3d. And that's what this is showing you. Titanium is right here. Okay. And these are the lanthanide and actinide series. So the same thing applies. If you have, for example, let's see, which one should I take? Cerium. If you have cerium, which is a lanthanide, its outermost electron is going to be in the 4f orbital. If you have thorium, which is an actinide, its outermost electron goes in 5f. So what you can do is you pick any element and then you practice writing its electron configuration. And there are plenty of exercises for you to do, practice problems. Okay. However, this is what we have to be careful, because there are some exceptions. And so the exceptions involve the transition metals. So if, for example, you had to write the electron configuration of vanadium, how would you write it? If we use the abbreviated version, where you use the noble gas notation, vanadium, the noble gas that precedes vanadium is argon. So you open a bracket, you put argon, you close the bracket, and then vanadium is on which period? 1, 2, 3, 4, on the fourth period. So it's 4s2, because you feel those two electrons that are in the s orbital. You have to put some electrons there. And then vanadium is on the third. So the third. So you have to put 3 electrons in 3d. Right? And then you can do the electron configuration for other transition metals. But what we are saying here is that there are some exceptions. So transition metals either have incompletely filled d subshells or readily give rise to cations that have incompletely filled d subshells. So copper, fine copper, you would have, if you follow what we said, you would write the electron configuration of copper as argon in brackets, and then 4s2, 3d9, because copper is in the 9th column. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where you find copper. But instead of writing that, copper is an exception, we put a bracket argon, so that there is no difference there. Then you put 4s1. So you take the one electron that is in 4s and you put it in the 3d. Why? Why do you do that? Because it is more stable when you have full d orbitals. Okay, so this is because either half-filled or completely filled subshells have greater stability. So we choose argon 4s1 3d10 as the electron configuration of copper. Same thing with chromium. This time it's chromium is in the middle. So if we were to follow what we said for the others, we put argon in bracket and then 4s2 and then 3d4. But 3d maximum number of electrons that it can take is 10. So half filled means having 5 electrons. So we take 1 electron from the 4s and put it in the 3d. Now you have a more stable system. So this is for transition metals. This is for transition metals. The same thing applies for lanthanide or the rare earth series, the actinides. They either have incompletely filled F subshells or readily give rise to cations that have incompletely filled F subshell. So if you were to take gadolinium, its electron configuration you would put would be xenon and then 6s24f8, right? But we know that the maximum number of electrons that an F subshell can take is what, 14, right? So half filled means removing one electron, right? So this is how you put one electron. You put xenon 6s2, so that doesn't change, and then 4f7, so you remove one electron and put it in 5d orbital. So it says here, use the Aufbau, this is a practice problem, use the Aufbau principle to obtain the ground state electron configuration of selenium. And the answer is what? So where is selenium? Yes, so it will be B. So argon, 4s2, argon in bracket, 4s2, 3d10, and 4p4. Okay. So here is a summary of the electron configuration. So let's take a look at the summary.
Electron configuration. Summary 1. Pauli exclusion. No two electrons in the same atom can have the same quantum numbers too. Each orbital can be occupied by a maximum of 2 electrons with opposite spins. 3. Hund's rule. The most stable arrangement of electrons in a nutshell is one that has the greatest number of parallel spins. 4. Paramagnetic atoms have one or more unpaired electrons. Diamagnetic atoms have all the electron spins paired. 5. In a one-electron atom, the energy of the electron depends only on its principal quantum number, n. In a many-electron atom, it depends on both n and its angular quantum number, L. 6. In a many-electron atom, the subshells are filled in the order 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d less than 4p less than 5s less than 4d less than 5p less than 6s. 7. For electrons of the same principal quantum number, their penetrating power. For proximity